We now start Chapter 3, Case Histories. First, an overview of the case histories that we will cover. Case history number 1 is about a two-phase gas liquid producer in the Trinidad region, and it will be followed by a single-phase multi-zone water alternating gas injector in the North Sea region. Case history number 3 is about the field-wide use of the optical monitoring systems in the North Sea region for two-phase liquid applications. And it will be followed by a demonstration of a conversion from a two-phase producer to a single-phase injector, a service change, again in the same field in the North Sea region. Case history number 5 is about the optimization of a multi-zone horizontal maximum contact well in the Middle East. This will be followed by case history number 6, a gas liquid application, a multi-zone high-rate gas producer in South America. And I will share an interesting background story on this case. Finally, case history number 7 is a demonstration of how water cut and flow rate optimization is achieved in a well in the North Sea region. So let's start with case history number 1. And it's a gas liquid application. The field is the Mahogany field of the southeast coast of Trinidad. And it is the largest gas producer in the Trinidad and Tobago. The production in this field started in 1998, and a two-phase flow meter was installed in 2002 in one of the new wells at the time. This well was a single-zone producer, and the downhole gas volume fraction was larger than 90%. All the details of the installation, the results, the challenges, and what has been done were reported in an SPE paper and available in the public domain. So here I will share 2 short but interesting stories about this case. Story number 1 is about the optical flow meter identifying a test separator error. So we have the oil phase flow rate plot here showing the oil rates for the months in 2002 and 2003. And we have 2 different data sets, one from the optical flow meter and the other is from the test separator. The blue markers are the real-time continuous data from the optical flow meter, while the red markers, the distinct data points, belong to the test separator, and the frequency of this data set was 1 test separator measurement every 2 weeks. So after the installation of the flow meter, which was around March 2002, for a good while, the flow meter data and the test separator measurements matched quite nicely. However, after about 8 months, there was an anomaly in this match. The optical flow meter started to show larger oil flow rates by about 200 barrels per day compared to the test separator. So checking into this issue, it was found that there was a leak in the test separator. So remember how we have discussed when we talked about the test separators in an earlier section. The test separators, they are very big pressure vessels, and they have many flange connections. And for that reason, there is always a potential for leaks. And this was a case which really highlighted that deficiency. So after fixing this leak, the operator created a success story out of this and shared this story internally within its organization. The bottom line was that this detection by the optical flow meter provided significant savings for the operator. That savings was in the order of millions of dollars. So let's move on to story number 2. And that is also interesting. And the story goes like this. 5 years after the meter was installed, the operator contacted us and stated that the surface instrument got damaged. And so they can't really get any data from the flow meter. The reasons for the damage were not made clear, but the region is a high hurricane-rich region. And we suspect that in one of those adverse weather conditions, there could probably be a power failure. So regardless, we brought a new topside instrument and connected it with the downhole flow meter. Once all the fiber connections were made, we started to receive the signal, and the quality of the signal was excellent. What we are seeing here is the power distribution for the velocity sensors and the speed of sound sensors. And if you remember, we have seen similar plots in earlier sections. The higher power distribution is shown by the red and the yellow colors. And in this case, we see ridges for the velocity and speed of sound signals. So the slope of this ridge, if we do a dimensional analysis in the frequency wave number domain, we are going to see that the slope corresponds to a velocity dimensionally. And it turns out that this actually corresponds to the velocity of the flow from the velocity sensors. And there is only one slope, as you can see, and that slope is the velocity of the fluid moving from reservoir to the wellhead. For the speed of sound, we can see two ridges, two slopes. That's because sound waves propagate in both directions. One family of sound waves move with the flow, and the other family moves in the opposite direction against the flow. So that's why we have two different slopes. So we can also compare the flow rates, the gas flow rates from the flow meter and the test separator data. And when we compare those data sets, we have seen that the agreement was within plus minus 3%. So after this very encouraging and excellent results, we have published a paper and presented it in 2 workshops in 2008. And that paper is available in the public domain. So the bottom line from these 2 stories is that the first story is about the optical monitoring system detecting an anomaly, so functioning as an early warning system, and in the process saved significant amount of dollars for the operator. In the second story, what we see is the longevity of the optical monitoring systems. After many years of operation and perhaps a year or so of disconnect from the topside instrument to the flow meter installed downhole, when we reconnect these two, we can see that the signal quality is there. That's because the optical systems are well known, as we have already discussed in earlier sections. They are well known for minimal measurement drift, and the accuracy is essentially preserved. So that is also a testimony to the longevity of the optical monitoring systems.